Welcome to this demonstration on electronic cooling using Autodesk CFD. We will be focusing on this Ember printer design to discuss how to observe the invisible characteristics of airflow in a virtual environment. Autodesk CFD is an upfront design-driven analysis tool. It provides the insight we are looking for at any point during the design process from concept to manufacturing. These results will help us to determine where improvements can be made to the design in order to extend the service life of the electronics in the product. They will also aid in reducing packaging size while maintaining performance. The traces you are watching are just one of many ways to visualize airflow. During this video, we will discuss other result types such as ISO surface plots. Create a 3D surface that represents a particular velocity or temperature of the air. Watch how easy it is to dynamically drag and drop the value and see all the areas of the design. Even show the direction of the flow on the surface by turning on vectors. Using Autodesk CFD, we can fully understand the performance of the components that are being used for electronic cooling. It is difficult, if not impossible, to acquire these result types by testing physical prototypes. Planes are another way to understand the flow at any location in the design. Add the plane and simply drag and drop it to another place. Even observe the temperature, velocity, pressure, and more. By dynamically translating and rotating the plane, we can search for ways to optimize the airflow efficiency. Once again, planes can also be shown with vectors, which is a great way to find vortices and dead zones in the airflow. The real power behind using Autodesk CFD is the decision center. As we make changes to the design, it is essential to know whether those modifications have improved on performance. This interface is unmatched. The view orientation and legend for the results are in sync between each of the viewports. There is no better way to make informed design decisions fast and easy. In this demonstration, we will not only compare the designs visually, we will use the data from each study to ensure that the temperature and volume flow rate meet our design criteria. Let's take a minute to discuss the Ember printer and design challenge. The Ember is designed by Autodesk. It is a high-resolution SLA 3D printer that uses UV light to cure the resin material and produces high-quality components in a short amount of time. Like many consumer products, the Ember began as a much larger size assembly without the fan seen in this animation. Due to the demand for a smaller footprint, the Ember design team was able to successfully reduce the packaging size 3 times smaller than the original. The challenge is keeping the parts cool. This includes the UV light projector, stepper motors, and various components on the PC board. The Ember 3D model is highly detailed, which is great for manufacturing. Using SimStudio tools, we can prepare our model for virtual testing in CFD. Open native files from major CAD systems such as CATIA, Inventor, NX, Pro-E, and SolidWorks. Let's take a closer look at the base of the Ember design where we have a bulk of the electronic components. After hiding a few parts, we can see the PCB contains detailed geometry for resistors, fuses, capacitors, integrated circuits, etc. Using SimStudio tools, we will quickly prepare the PCB for analysis. Let's colorize the individual bodies to make it easier to see what we are looking at. Let's also show some of the information about this assembly. We have almost 5,000 faces, many of which are not necessary to mesh and solve the CFD study. By choosing a size, we can find all the parts that are smaller than 2.5 millimeters and quickly have them removed. Once again, we can see some of the components on the PCB contain a significant amount of detail. SimStudio Tools provides a feature for replacing these parts with a primitive solid, which is great for the analysis. You can see here the size of the body is automatically based on the existing geometry. Or manually drag the size and even choose the shape of the solid. SimStudio Tools even recognizes copies of patterns, greatly decreasing the time involved when simplifying multiple instances of small components. With very little effort, we have already removed half of the faces in this model from 5,000 to under 2,500. Upon completion, it is down to under 900. We have a higher quality model that accelerates meshing, solving, and evaluation of design alternatives. Back in the main assembly, it is common to see extruded text or logos on consumer products. These features are automatically detected and deleted using remove features, once again saving time on mesh creation later. Now that we are finished, it is just a matter of sending the assembly to Autodesk CFD. By spending a few minutes in SimStudio Tools, we have a model that is highly efficient. That means less time meshing and solving, leaving more time for innovation to make better products. The setup in Autodesk CFD is intuitive. The ribbon takes us step-by-step through the process of specifying materials, boundary conditions, and mesh settings before running the solver. The editing options in the graphics view are always in alignment with the current setup task. Autodesk CFD contains a large database of material models to choose from. Specialized model properties are created specifically for high-fidelity results in electronic cooling. In this list, choose items beyond fluids and solids. We will also find internal fans, centrifugal pumps, PCB compact thermal models, LEDs, thermoelectric coolers, heat exchangers, and heat sinks. All these models reduce the amount of effort needed to draw detailed features and apply proper boundary conditions. We have a few parts that are generating a significant amount of heat. The two stepper motors will be set to 10 watts each. Then there is a UV light projector that is outputting 20 watts. There are also various components on the PCB that we have already applied heat power to. Mesh sizing is an important part of the setup for getting accurate results. Here there are some areas on the model that may require more attention. For example, the heat sinks play a significant role in dissipating heat from the UV light. We want to make sure we capture the airflow accurately. Upon editing, Autodesk CFD provides a preview of the mesh size before it is generated. The solver contains several settings for calculating airflow and heat transfer. There is an option for steady state and transient studies solved over time, as well as the capability to solve in the cloud. This is a great option for running studies during work hours when we need computer resources for other tasks. Scenarios that are run in the cloud are solved simultaneously so we can acquire results on several design scenarios faster. Our first scenario is a natural convection problem without the use of fans, so we will have heat transfer selected along with gravitational effects. Let's begin by taking a look at the cross-section of the air. Currently, we are observing temperature results for the components as well as the fluid volume. We can see the warm air naturally move to the top of the base. How about velocity? As we drag the plane over the vent on the bottom, we can observe the air entering the system. By changing the direction of the plane, we can noticeably see the pattern of the holes on the base. Right now we are using a fringe plot. It also helps to use vector settings and observe the direction of the flow. Not only can we see the direction of the flow on the 2D plane, the vectors are displayed out of plane providing a 2.5D representation. Earlier we were looking at the traces coming from the fans. Placing them on the design is fast and easy. Simply choose the locations on a plane for each trace, or even create a circular or rectangular pattern. The rectangular pattern works great for the vent we are using on the base of the printer. They clearly show the behavior of the air from the inlet to the outlet, and they can be displayed many different ways. Now the big question: we reduced the size of the Ember printer 3 times smaller. Is the natural air convection enough to cool the stepper motors? Checking the temperature of one of the motors, we can see it gets as high as 162 degrees Celsius. Certainly with a more compact design, it looks like we are going to need to install fans to move the air in and out of the system faster. Let's go ahead and take a look at them using SimStudio Tools. We will section the model to have a closer look. Like many purchase components, the 3D model can be downloaded from the supplier website, and the parts may contain components or features that are not necessary for running the CFD study. Watch how SimStudio Tools quickly prepares the geometry before sending it back for virtual testing. Taking a few minutes to remove detailed features saves a significant amount of time depending on the number of design variations we plan to run. With a fan, we are only interested in a simple case with a separate body in the center for the fan material model we will apply in the CFD scenario. As you can see, the interface for SimStudio Tools is intuitive. Sketches can be reused for multiple features, and each extrude feature can be specified as a boss, cut, or additional body. The canvas allows users to drag and drop the depth or choose the geometry to extrude to. This is the way the design process should look when creating new parts or making modifications. The fan is now ready to send to Autodesk CFD. SimStudio Tools recognizes multiple instances of components in the assembly. Any changes that are made to one of them will be reflected on the rest. We have another design scenario in our CFD study that contains the fans. Let's hide some of these external components and apply the material models for all three of them. First, we have the cooling fan for the heat sinks attached to the UV light projector. Notice all the properties we need are available for the fan curve, rotational speed, as well as slip factor. There are many fan models included in the material library. Otherwise, fan curves can be entered in manually from specs found in the manufacturer's catalog online. We have a 4300 RPM fan that is used to direct air underneath both of the stepper motors. We will run two scenarios with two different size fans from the same supplier. One of them runs at 4300 RPM and the other at 2500 RPM. In the plane contour plot, we can once again observe the velocity of the air entering from the fan and leaving the vent in the rear. Is there enough airflow in areas where cooling is needed? Do we need to direct the air or adjust the locations of the fans? Let's also show the vectors to find any areas on the model that are hindering airflow or search for dead zones. XY plots are a great way to gather data from the plane. Simply choose two or more points in the graphics view and specify the amount of data to collect between each location. The plot can display any quantities such as velocity, temperature, pressure, and more. The summary checkbox will enable us to show results for all designs and scenarios in one plot, which we will see in a few minutes. We know the fan is going to cool the stepper motor more effectively. The question is, how much more efficient is it? Choose any of the components from the design and check the average, minimum, and maximum temperature values. We have dropped the temperature down to 56 degrees Celsius, which is great. However, the 4300 RPM fan may produce excessive noise. So we have also run a study using a 2500 RPM fan from the same supplier. Using the quieter fan, we are looking at 78 degrees Celsius. Our goal is to keep the temperature below 70 degrees in order to extend the life of the printer. Perhaps we can still use the quieter fan if we make some changes to the design. In an effort to reduce the system resistance, we will make some changes to the vent in the rear using SimStudio tools. We have added smaller holes between the larger existing ones. Let's also extend the length of the vent for additional exit points for the airflow. This should reduce the system resistance and lower the amount of pressure on the fans. The question is whether it will improve it enough to install a more energy-efficient and cost-effective device to cool the motors. Before we look at temperature results, let's pull up the Decision Center and compare the 4 different scenarios that we have solved. At this point, we will leave out the initial study using natural convection. Viewports are a great way to compare the various plots. Does the fan size or geometric changes have an impact on the airflow and temperature? Already, we are observing better performance in Design 2 with the larger vent for both of the fan sizes. We have several plots created to make sure we choose the best design possible. Here we can clearly observe the flow between the fan and the rear vent. If there are any dead zones, it may be interesting to show the velocity vectors to better understand the direction of the flow in those areas. And finally, the isoplot seen here displays vectors at a particular velocity. This helps us to understand why some parts, such as the stepper motor and PCB, are cooled more effectively. Ultimately, that is what is important to us. Let's have a look at the actual temperatures of the UV light and motors, as well as the operating conditions for the fans, such as volume flow rate and pressure. We can see the temperatures listed for each of the components that generate a significant amount of heat, or show a graph to easily compare the values for each design. We can see that the UV light projector temperature in Design 2 with the 2500 RPM fan is almost the same as Design 1 with the 4300 RPM fan. The stepper motor for Design 2 also meets our requirements. The pressure drop on the 2500 RPM fan is 3 times lower while still providing an effective volume flow rate and improved energy efficiency. It looks like the larger vent with the additional holes is enough to reduce the system resistance and allow us to utilize a quieter fan to cool the components. And remember, the XY plot is also available in the Decision Center to compare the velocity and temperature of the air exiting the fan. We can once again see how Design 2 with the larger vent is outperforming Design 1. As you have seen in this demonstration, Autodesk CFD enables designers to see the invisible characteristics of airflow in your design. It is your upfront design-driven analysis tool for making informed decisions early in the concept and design cycle when making changes is most affordable. It is your trusted solution for fluid flow dynamics, and it is the future of making things.